Okay, go ahead.
Well, welcome to the December 8th, 2020 session of Tangerine SDR and HAMSI for development of the personal space weather station. My name is Dave, KV0S, and this week I've had a magnetometer in the ground since last Saturday. The only thing that I did write some software. First, I had to write some Python code to convert Dave's output to something that I could read into R. And I did some plotting in R, and I'm not getting a lot of um, variation in the magnetometer values. They look to be in the right scope. The temperature values are going up and down. The remote one is going up and down. The in the shack one is sitting here on the table, so it doesn't fluctuate nearly as much. Interestingly, it's warmer than my other thermometers say the shack is, so I'm not quite sure. And I had a little bit of problem with this before, and I'm kind of curious if Dave has his revised code available yet. So we'll look into that. So let's go down the list. That's about it for me. I'm going to try to keep the roll call as short as possible so that we have time to go on to subjects. Okay, next on the list is Nathaniel.
Thank you very much, Dave. I've been finished up the semester finally last week with all the grading, and I've just been working on data analysis for the AGU meeting and trying to get caught back up with research tasks. So back to net.
Fine business. And next on the list, we have Dave, KD0EAG. Go ahead, Dave.
Hello. Um, yeah, I've been working on code. Um, I got a little distracted the last few days. I was away some of the weekends, so I had to get away from things. I too have been running one of the magnetometer pairs pretty consistently, and but I'm not sure if it didn't stop sometime on Saturday, but haven't got to the bottom of that. I kind of got distracted because I got into some code weirdness on my main machine here. And finally, I think I figured it out this afternoon. It's just this evil squirming anaconda or conda thing that I was using to install um, Python stuff, and that, and it has some kind of treacherous features.
You
that
aren't watching John Gibbons. He's
yes, yes. There's some things that are just, it's like, who stole my machine or who's hijacked
Uh-huh.
it. Yep, yep, yeah. And
Oh,
I I couldn't, yeah. But I discovered how to kill it, and or at least how to stop it and
that's
use
the
it when I
easy
want.
part. Fixing it's the hard part.
Pardon?
Killing it's the easy part. Fixing it's the hard part.
Yeah,
yeah.
yeah. Well, it's working, but it was just working when I didn't want it to, and strange things would happen, and whole libraries would appear and disappear. So anyway, that was plaguing me because I was trying to write some code, at least for my sake, to automate the analysis of some of these logs, and all of a sudden things weren't where they're supposed to be. So that having been resolved, I suspect I've got some new code. I don't know. Maybe I can get it up there tomorrow and reveal it in all its splendor for someone to test besides myself.
Well, I
But
have been watching your list.
yeah, well, I haven't. I can actually make it send you a notification, but I haven't. I've been wanting to keep it to myself for the moment, and I was wanting feedback from people about what options they were using, and it took a while to think I may have have a sense of what that was, but what those were. But anyway, I'm sure people will have other things to say about it once I make it available. I just have to make it public. That's it for me. Thanks.
Okay. Next on the list is John Gibbons. Go ahead.
Been a busy week. Class is finished up, and I spent the entire day today grading senior projects, so that was fun. The personal space weather station for Maxwell out in Fort Collins, Colorado, shipped on Friday. He should get it Wednesday. Had some issues with calibration, but I figured it out. I was off 0.152 hertz on 10 megahertz, and I got it down to 0.001. So he's set. Behind me, in fact, if I do a real quick, oh, come on. This is somebody we know here, node number 14 running. If you notice the thing up there.
Mm-hmm. Yes.
In Lackawanna County, that's really weird. So I've got this system running. I discovered that I ran out of the SD cards, so I ordered some more today because the original ones I ordered, they were from a fraudulent buyer, and that sat for a week, and I forgot about it. So I got new cards. They should be showing up Thursday. Otherwise, Nathaniel, your station would have been shipping tomorrow morning. But I've got yours, and I'm making a second one for somebody else that's you're going to distribute to.
To Gareth, maybe.
I'm not sure. I'll have to look at the list that Christina gave me, but I'm shipping 2 units to you with next.
Okay.
So it'll be units 2 and 3 of the list of 10, I think.
Wonderful.
I have updated the personal space weather station documentation section for the Python code that does the entire file directory structure creation for the PSWS system. And it also creates all the metadata files. And I fixed an oops where I was assuming it was in the PSWS S code directory, which is one of the directory it creates. So it's like the chicken and the egg thing. So I put it in the root directory and fixed that because the copies I'm making already have it there. So I didn't think about it. But if you want to create a new one, this will now work. That's all up on the website. I did get a chance to look at Bill Engelke's C code. I have a lot more respect for Bill and what he does. It's been a while since I've looked at all those pointer thingies, and you're amazing, Bill.
Yes.
So back to Nut. I've been busy.
Okay. Thank you. And next on the list is Bill, AB4EJ. Go ahead, Bill.
Oh, good evening, Dave, and good evening to the net. Been fairly busy here. I added something to the Tangerine local host so that it outputs IQ samples to a UDP IP address and port of your choice. And so now I've got a GNU radio which is able to read that port. And so now I've got the local host interfaced to GNU radio. Now, I want to get some, once we get into the open discussion, I need to get some input from people who know GNU radio better than I do, because I want to get it to where its output is comparable with Spectrum Lab. I know what I would have to do to make an adapter to pick up Spectrum Lab, pick up this data and feed it to Spectrum Lab, but that is, I'd like to avoid that if possible, because it's a Microsoft thing. And yeah, anyway, so once we get into our open discussion, I'll show that, and I'll show the layout of the GNU radio GRC or SRC or whatever it is file that I have, and maybe get some advice. Also working on some stuff for Nathaniel on preparing some data, and also trying to work with Dr. Atkinson on finishing up the final report for the BSWS project for this year. So back to Ned.
Fine business. Next on the list, we have Dan in for XWE, our Raspberry Pi Zoom guinea pig.
Yeah, well, thanks, Dave. Hello, everyone. Yes, I'm using a Raspberry Pi. I think it's jerking and twisting and not real smooth, but it seems to work. It's only crashed once so far. So anyway, this week I did work a little bit on scripts, and I redid all of the Raspberry Pi scripts to the latest version of whatever software was being installed. I think I've got FLDigi, WSJTX, I don't know what else, HamLib, a number of other uh, applications that you can install with a script. Anyway, that's about it from here. Back to you, Dave.
Fine business. And next on the list, we have Dave McGaw in one HAC. Go ahead.
Hello, all. Been working on various work projects this week, ground and rocket and CubeSat and all that above, but did have time to bring up the new magnetometers, and those are working, and I hope to get one sighted outside to let it run for a while. Back to Net.
Very good. Next on the list, let's see, is Dick, K2LCT. Go ahead, Dick. Are you there?
Yep, I'm here. Nothing to report from Phoenix. Back to Net. Back to you, Dave.
Fine business. Next on the list is Homan Kim. Go ahead.
Good evening, everyone. It's been a while since I actually sort of disappeared. My class went from 6 to 9. So after my class is done, I was completely exhausted. I have like multiple classes in one day. And now used to be converged mode where I have to be in classroom to teach. Now after Thanksgiving, we have coronavirus surge. So in Newark, there's a new curfew order. So the campus is now off limits. But otherwise, I don't really have anything to report in particular. I'm working on the installation documents. So for those who receive the package from Scotty, we will have to follow some certain installation procedures to make sure that we have all the same sensor orientations whatsoever. Otherwise, yeah, I did receive Scotty's package. Thank you very much. I had to actually go to the campus to pick it up because right now it's in curfew right now. So yeah, things are going slowly. I finally finished my last lecture today, so that's why I'm able to join you guys again. So glad to see you, and then I'll keep working on this document.
Welcome back. Yes, I'm off of teaching now. Last week was our last in-person week, so we're finishing mostly assignments, and we had 3 days of class this week that are Zoom if need be. Anyway, back to James, KD4 DSG. Go ahead.
Yeah, I'm here. Not much to report. Listening in. Back to Net.
Okay. Next we have Jonathan, KC3 EEY. Go ahead, Jonathan.
Hi, everybody. I don't really have much to report this week. I was looking at some grad school programs. Other than that, I was busy with the AGU fall meeting. That's about all I have. Back to the net.
Fine business. Next on the list is Jules, K2KGJ. And I know Jules has been busy.
True, true. I spent most of this week actually cleaning things up. I'm rerouting Cat5 cable to a more convenient location for the 2 Raspberry Pis that are going to be collecting data. I've got about 7 days worth of data from the new mag that I still have to analyze, and about 5 days from the dual installation that I have to analyze. I haven't gotten to that yet. I just received today my first Pi Uptime UPS 2.0, which is the same unit that Dave's going to be using to try to get around the problem with power drops on the line coming into the house. Other than that, that's about it to report for today. Back to net.
Fine business. And let's see. Next on the list is Michael, AAAK. Go ahead, Michael.
Greetings to everyone on the conference. Back to you, Dave.
Fine business. Next on the list is Scotty, W2DFI. Go ahead, Scotty.
Okay, thanks, Dave. Not a lot this week. I've been working with Tom on the clock module some, Tom and John, and did prepare a report on the progress to ARDC for our grant, since they want like a quarterly report. So I had to get that going. And Jules, I'll send you out a board in the next day or two that has the end-fed connector on it for your wiring pleasure. And,
That's great. Thanks.
You're welcome. Back to you, Dave.
Fine business. And so we come to Tom, our usually our last person to talk on the
Bringing
list.
up fear yet again.
Yes.
Not too much. I started reading the paper about the sporadic E measurement system. That's an excellent document, extremely well written. And I think there's a lot of tips for Tangerine SDR that can come out of that document. So back to the net.
Very good. So I think I've gone through everybody.
We're getting some breathing on the line here.
The open mics are Dan and me and David McGaugh.
Thank you.
So, and let's see. So, not missing any new ones. We're open for general discussion.
One thing I forgot to mention to Nathaniel is that I uploaded over 1,000 data files to the Dropbox for my 2.55 and 10 megahertz data collection since well, 5 has been since April and the other 2 has been since July. So the plots and the data and all that stuff are up there, which I believe would be for, I forget his name. Your grad student.
Mike.
I think you're
Nathaniel.
muted.
Okay.
There
Yeah.
you go.
Okay. Yeah. I think I actually did see that. I'm not sure. Hold on. Which Dropbox did you put that onto?
It's the one that Dave Kazan set up through Case.
Oh, okay. Because I'm looking on through Case.
Yeah.
Okay. Because
We can invite you to that. I think we'll probably have to do that.
I'm looking at this right now. It's not these, is it?
That is an old one.
This says updated yesterday by David Kasdan.
Okay, well, I guess mine's not showing up. He must not have shared it. I guess it's in that one there. I'll have to see what's going on.
Okay.
There's something goofy going on. So yeah, it's probably just I have to click a button and let you get access to it.
Sounds good.
One other question for, I think it'd be Homin, concerning the orientation of the magnetometer when you put it in the hole. I'm wondering, does it really have to be aligned at all, since we're really looking for relative vectors and not absolute? Because everybody's absolute vector, depending on where you are on the Earth, is going to be completely different. Because I know mine points down like 60 degrees down. where I'm at in Cleveland. And aren't we looking for relative movements, not absolute position for the data collection? I guess what I'm getting at is if you cal the thing and we took a vector that was like 1,000 samples of X, Y, and Z and called that our reference vector, and then every measurement was made by subtracting a vector off. So you always came back to zero, and then you could see what all the perturbations were from zero. That way everybody would be showing the same scale and measuring the same thing. Is that not what we're after, or am I misunderstanding the experiment?
I'm not so sure if I understand the entire thing that you mentioned, but yeah, the relative measurement is the key. Actually, we don't really. So you're talking about the absolute background value, or
I'm actually talking about the actual orientation when you put it in the ground. Like,
yeah, I was wondering about that too. How accurate are we really needing to be? I don't think it has to be to a fraction of a degree.
It doesn't have to be that accurate, because I have seen some pictures where they have the levels, X and Y levels, which, I mean, once you take the relative or the calibration vector, when you stick it in the ground and call that your reference, it doesn't really matter if you're off a degree because it's caled out by the calibration vector.
yeah, yeah. So what we do, I guess I mentioned this before. What we do is to, especially you find the leveled position for XY plane, right? Has to be leveled. And then you rotate the sensor until you see the maximum value in x-axis and minimum value in y-axis. How accurate that has to be? I mean, how accurate can you go? I mean,
yeah.
During the storm time, it could be off by many nanotesla. So you can't really be that perfect, but that's what we do. Like maybe oriented to see a maximum in x, minimum, not minimum, zero, close to zero at y-axis. You set it, watch it. Maybe next day, maybe it can be off because maybe you measured that during the storm time or something. So maybe you do it maybe a couple of days or something. Then let it go. I think that's good enough. I think.
But John, you're talking about a more general, just put it in any old way and look at that vector then?
Not any old way, but it doesn't have to be accurate to 1 or 2 degrees. If it's off 5 degrees, I mean, your relative movement's probably going to be less than a degree, I would imagine, on any axis.
Oh, okay, yeah, but that's.
I'm also wondering why you wouldn't want to orient it to true north, because all the measurements are given as deviations from that.
What Humin just described was magnetic north.
Yeah, that's setting it to your local magnetic north, which is variable.
Yes.
Well, that's just the whole point. I mean, we're looking for relative movement of the magnetic field. It's not absolute.
Right.
So once you set it in the ground and fix it and it doesn't move, you take your reference vector and that gets subtracted from every measurement you make. And ideally, you always get zero unless there's a perturbance.
Right. So local magnetic north, relative value of vector, that's fine. And total degree error should happen, and it doesn't really matter, I guess.
But, okay, so say 4 or 5 degrees, something on that order, is not a problem. There have been some who've asked.
But also, I don't think that our sensor has that much of accuracy in terms of degree.
Sure.
We're talking about like really high-end flux gate magnetometer that has like, sub-degree accuracy, directional accuracy. Yes, but I guess this is such a small.
Yeah, if you look at the board, the sensor board, and pay attention to the z-axis sensor, it can be on the 3 or 4 boards I've looked at, it can be off by as much as 2 degrees from the vertical to the board.
It depends on how it is soldered, right, onto the board.
Yes.
Right.
But I'm trying to anticipate the question. Some have asked about whether we needed to, why we needed to align it at all, and why we couldn't just fix it in software, so to speak. And I doubt that that's probably a good thing to do. But I haven't.
That's what I've been sort of suggesting that we do, because everybody's reference is going to be different. Just by the way the Earth's magnetic field is round and your location on the Earth.
So you could just lay it on the ground.
Long as it doesn't move, I think that's the important part. Once you calibrate, as long as it doesn't move, you're fine.
And I'm still curious why you don't orient it to true north instead of magnetic north. Magnetic north is going to be always moving.
Yep.
So it's true north relative to magnetic north.
Yeah, and you know the numbers that I can get for my location are relative to true north. And yeah, we have a 15-degree deviation here.
And that brings me up to the next question. This is the perfect group to ask. Magnetic declination, if it's specified as positive, like in Cleveland, for me, it's +8 degrees. Does that mean true north is at +8 degrees and I'm sorry, magnetic north is at +8 degrees and true north is at 0? So I go right.
It's
a good question.
It's to your west.
Because I was trying to set my azimuth elevation rotor, so I either got it right or I'm off 16 degrees.
So
yeah,
it's true north. Magnetic north is to the west if your declination
is positive or negative.
So your 0 goes through Missouri. So if you're out in Portland, Maine, it's like 20 degrees to the west. And if you're in Portland, Oregon, it's 20 degrees to the east.
And that's the magnetic north is, well, for here in New Hampshire, magnetic north is 15 degrees west of true north.
Right.
I'm thinking Cleveland, it's 8 degrees. I want to say
West.
It is west?
Yes.
Yes, it would be because
I'm looking at the map now.
the 0 line goes through Missouri right now.
Okay.
And when I was a Boy Scout, it was 5 degrees east.
When I started the azimuth elevation rotor in 91, it was 3 degrees. And it's now moved up to 8 degrees in 30 years.
So if you look at, there is a map of the track of magnetic north, and it used to hover around Hudson Bay, and it's made a big shot up towards the polar region, and it's actually creating a little hook.
So do you guys think that it makes better sense to orient the sensor along the true north line and then apply declination angle depending on where you are?
I disagree with that because it's going to make the installation much more difficult. Going to magnetic north means you're maximizing the vector on what you're looking at. That's easy to do.
Right.
I don't see any reason to offset it by the magnetic declination because that's not what we're after. We're after the actual magnetic field.
So I think that's I mean, we don't really have anything that is set in stone in terms of insulation orientation, but I guess that's what we do in the field, especially in Antarctica, because you know we don't want to bother to look at like measuring the true north, whatever.
Right.
We measure local magnetic field and assuming that the field is not changing that much, but also we're interested in relative variation, so we don't really too concerned about the absolute location direction of true north.
So to completely understand this, a positive magnetic declination correction would mean that that magnetic north is -8 degrees from true north. If the
Correct.
magnetic declination correction is +8 degrees.
Yeah, because what they're actually doing is going from magnetic north, which you can measure locally, and telling you which way do you go to find true north.
Okay, so then, gotcha. So I should see, it should be.
So when you're using a magnetic compass,
you can
true north will be 8 degrees to the east of.
You can rotate the dial on a magnetic compass so that it points to true north.
Right. I just got to make sure I pointed it the right way because I've done it backwards.
Yep.
Yeah.
Well, just remember it's west of you.
Okay, it's west. Thank you.
I have a question about the orientation forced by the board. So when I put mine in the ground, I put the board along the direction of the pipe, which forces the north arrow to point straight down.
Right.
And I'm putting it so that the components on the board are on the east side of the board. And I'm orienting the surface of the board north and south. Jules, is that how you do it?
Let's see. What I have is the board. If you take the board, let's say, and point it to magnetic north, and then you turn the board 90 degrees about an axis that runs through that's perpendicular to the north-south line. So now north is pointing straight on the board, is pointing straight down.
Correct.
Z
This
is
way.
pointing straight. Z is pointing toward the north, and
So
the
the part's
y-axis is
pointing
the
north.
same.
So
And
the
the
part-
y-axis, pardon me?
So you have the plane of the board east-west.
So you're
Plane of the
talking
board
about,
is east-west. That's correct.
Oh, okay.
so you're
And the
talking
parts
about
are
the
on the
one
north
that's
side.
sticking
And
out of
so-
the board.
So Z becomes the north, becomes the
Okay.
x vector, actually becomes minus x. Okay.
So this is
Because
Z, right?
it's pardon me.
This is, I mean, by the instrument standard, this is Z component, and then you actually orient this
Correct.
Yes,
towards Z axis.
correct.
Okay. Then I'm 90 degrees off the way
So-
I
Well,
put
you
mine
can
in.
just relabel your axes and you're fine.
See here.
Yeah, well,
So my
But
board
you
right
want-
now would be pointing north. Because it's actually pointing down for north. Because north would normally be like that.
correct.
You say
Right.
rotate it down. So this would be facing north now.
Correct.
Got
I
it.
think there should be a configuration in the file that tells what the actual orientation of the board is. I don't know if you
Yes.
need to do it just the 3 orthogonal axes as to whether it's north, south, east, west, up, down, or we could, as was said before, you could put it any arbitrary one and then somehow figure out what.
Well, if we get it
those
backwards, that means the
rotations are.
perturbations are going to be measured backwards. We want all the perturbations to be in the same direction.
Right.
But if you say the actual board has north pointing down and the tall part that is the magnetic sensor for the vertical axis is actually pointing north, which means the parts on the board are pointing north, everybody will be the same.
Correct.
Yes.
Z becomes x becomes minus z, and z becomes x. So yeah.
Yes.
Yes.
So
And
this the board side, the top side of the board is facing north, right?
yes.
Correct.
Let's see if I can get that to focus. No, well, anyway.
So we are
I've-
north of you when you were
Oh.
holding it a minute ago.
Right. I am facing north with the board right now.
Yes.
Now, I will say generally, if you just put it any way you want, do it, something orthogonal that you can. And then you know what position you are on the Earth. You can look up the standard magnetic field and figure out what orientation it's been mounted.
Okay.
So when you generate files, you're going to have some kind of header saying which way the board's
Yeah,
oriented.
that's what I'm saying. Need some kind of orientation
Yeah.
info.
That would make it easy so you don't have to figure it out.
Hmm.
Well, and then everybody looking at files is going to be able to use the data the same way.
Yes.
Because if it's all skewed all different ways, then somehow they're going to have to correct the data before they analyze it.
Well, one thing that I could do is in the local host, provide an orientation guide, which would step you through getting your z-axis aligned with magnetic north.
Actually, what you could do, Bill, is just they send you with each data set every day the calibration vector, which tells you which way the board's pointed. Because if they got the part facing north and it's down, it's correct. Or if they have it flipped around,
Well,
if the N is pointing down, you got one or two orientations you can work with.
one reason I've been slow about getting a new set of software out is because was anticipating some metadata specification that I assumed would go at the beginning of every day's file that would show the critical parameters, which
That's
would
what you're waiting for
essentially
me,
address this problem.
Yeah.
But I don't, for one thing, I haven't been able to figure out what, I don't know. There seem to be lots and lots of Dropboxes and Google drives and things, most of which I don't have any access to or any information about. And so I don't know where anything's being put. And so it's kind of hard to code according to it. But then again, I kind of suspected that it hadn't entirely been decided.
This, what
if
I have
someone
on,
if someone figures it out, could they let me know? That's
what I have on the screen right now, and the link I put in the chat is the IAGA Guide for Magnetic Measurement and Observatory Practice. And so this is actually a guide which spells out how you're supposed to run a magnetometer on the ground. And if you go to chapter 8, which I think is like, just had it, there's 7.5. Testing and calibrating instruments. So they talk about in here both using magnetometers for just measuring the variations, and they also talk about using magnetometers for absolute field measurements. Now here it says for the magnetometer where you're using variations, they talk about having the 3 orthogonal elements of the magnetic field for each of the 3 sensors, which is exactly what we have. And it says rule 1 is vertical, and one of the horizontal sensors is pointing towards either the geographic or the geomagnetic north. So actually both pointing toward geographic north and pointing toward geomagnetic north, both are accepted standards. So you can do either one. And then it goes on to say that in field work, and for example, in C-bottom magnetometers, any orientation is acceptable. It is only necessary to know the azimuth of the variometer. In all recording practice, it is necessary to know the corrections to the data if the sensors are not orthogonal. And so then they go through with some nice diagrams here, and then they have the math that lets you map from one orientation to another. So I think if we have any questions regarding how to run our magnetometer, I think if we refer to this document, we're going to be in a pretty good spot.
Yeah, Nathaniel, it's the same document I've been using, the same guide.
Okay.
Daniel, can you provide a link?
Yeah, it's in the chat already.
He did.
It's the first link in the chat.
And another site, if you haven't looked at it already, is www.intermagnet.org, which also provides a copy of that too.
But actually for Bill, if he got the calibration vector, he can then determine if Z is pointed in the correct, down, basically down, and the orientation of the board should come from X and Y, knowing the latitude and longitude. So he could actually self-correct for all of them. Even if you got it in backwards 180 degrees, you could self-correct for that.
Yeah, I think the more self-correcting we can build into the software, the better, because I don't think it's reasonable to expect a large-scale citizen science project of high schoolers and volunteers doing this for fun to get the orientation right on all of these things reliably.
Ideally, you'd like to just be able to put it in the pipe facing down, stick it in the ground, and let the software figure out where it's pointed.
Yeah.
Right.
Yeah.
Which if the metadata contains the calibration vector, you're golden. So
how do you calculate the calibration vector?
Once you put it in the ground, you make 1,000 measurements, take a standard deviation, and that's your X, Y, and Z measurement for 0.
But you look for a 0 toward magnetic north.
You create the 0 by the vector you're measuring, because then every measurement you take, you subtract off the calibration vector to get back to where you want to be, and that's the magic.
Okay.
So you basically you don't get a measurement that you can Well, what's our sample rate? It's
1 hertz.
one. Yeah. So you need 1,000 seconds.
I think you need to do it over a longer period of time than that.
Probably the longer you run it, the better off you are, right?
Yeah, but I'm just thinking in terms of geomagnetic variation. You
Yeah.
want you want to do it at a time when
It's
the magnetic field is relatively stable, and then you want to average out long-term noise.
Yeah.
Judging by variations that you can look at on intermagnet in terms of various locations and fields. And Homan, perhaps you could enlighten us on that. It looks like something in the first few hours after 0-100 UTC is probably a good time to look at it.
And 1,000 samples is only 16 minutes.
Yeah, you could have a wide variation that would hold easily that long.
Mm-hmm. Well, if you have any sort of geomagnetic storm going on, geomagnetic storms can last multiple days.
Right.
So like solar flares and WWV, same problem.
But
those would be documented, wouldn't they?
Well, it's the same sort of problem you have with a rheometer. You have to average over quiet days.
You look at the intermagnet site and look at several days of locations that might be near you to get an idea of what the diurnal variation is, and you can find some fairly quiet days.
But even under disturbed conditions, doesn't it tend to average out or not?
Yep.
Okay.
I think over
there
20...
also, depending on where you are, there can be preferred directions of auroral currents that will give you a bias.
Hmm.
Yeah, that's probably true.
Need an action plan. Need to know what, at least a starting point recommendation for what we should do. And then should this go in a file that gets read by the on the local machine for the time being? Every time we start writing a new log file.
How about this? Suppose it's fairly easy to get a level surface. I mean, for a couple of bucks, you have a good spirit level.
Mm-hmm.
If you can just level the board itself, let's say the surface of the board, if you want to orient it that way, or if you rotate it 90 degrees up on end, just make that level and don't worry about the other orientation. That is the third orientation. That should simplify your calibration.
Mm-hmm.
Yes.
Mm-hmm.
The only caveat I see with that is the pipes are going to be vertical, which means the board orientation is going to be vertical and not horizontal.
Yeah, but that's okay. Now, what I'm saying is, John, no matter whether you've got the board horizontal or whether you have it vertical in the pipe, if it is aligned properly with the axis of the pipe, it's pretty easy to get that pipe vertical to within a couple of degrees. If you do that, then don't worry about the north.
So you get one axis calibrated and the other two you could figure out.
It'll be close enough.
I have a question. The default sampling is what, 200 samples, and I know Jules is using something faster.
I was changing the default to 400.
Okay. Is that a reasonable thing to do?
I think so, based on what I'm seeing. And also, you want to get really good data down to close to 10, 5 or 10 nanoteslas. You have to take 1 minute rolling average of that 1 second data.
Okay.
That's 400 samples?
400 samples, yeah.
Okay. Nathaniel,
and it even helps to
but
average that.
The software does this.
Right. What is the 1 tau of a event that we're measuring a magnetic interference with? How fast does it change?
Again, that can depend. There's different time scales of them. So
1 second fast enough?
Oh, is 1 second fast enough to measure these things? Yes, 1 second is fast enough. Yes.
Okay, so that'll cover most of the stuff
Yes.
we're looking for.
Mm-hmm.
Okay.
Yes.
And
Yeah,
then
one second.
you're measuring 200 samples in 1 second, correct?
Yes.
And then
Yeah,
that's your one data point.
And
Yeah.
what we're recommending is 400 samples in 1 second.
Okay.
that's more than enough. Most high time resolution magnetometer observatories for space physics do 1 second resolution.
Nathaniel, what magnitude of change are you looking for in that 1 second?
That could depend. You know, the smallest things we're looking for are going to be on the order of, you know, a few nanotesla to fractions of nanotesla, which of course this particular board doesn't cover. But that is kind of the smallest thing that we'd be looking for. And the largest things we could be looking for would be like, you know, 600 to 1,000 nanoteslas.
Okay, well, what I've been observing with a count of 400 and then an average, which is built into the magnetometer of 10, I was averaging 10 of those, which takes 150 milliseconds. My noise band is 10 nanoteslas, so I can't see anything any better than that.
Okay.
At a 1 second resolution.
Okay. Yeah, which is
at the rate of what, the 400 samples per second?
That's 400 samples per second, and then using the averaging feature, taking 10 averages within the magnetometer itself, that whole process at a 400 sample rate and 10 averages is 100, actually it's 135 milliseconds.
Where did you get the number 10 nanotesla resolution? Is that what was written in the spec sheet, or?
No.
No, that is actually from the spec sheet. Is rather vague, but actual testing, if you look at the 1 second samples and just graph those over a period of several minutes, again using a 400 count with an average of 10 for each point, you see a noise band, at least in this area I do, of approximately 10 nanoteslas rather peak to peak.
You've got a rolling average of 10 samples per at a 400 hertz rate.
That's right.
You're taking 40 samples per second then? Or 400 that are averaged over plus or minus 5 from the one you're at?
Well, you're actually taking 10 samples at a 400 count in 132 milliseconds.
Okay, so it isn't over a second, it's 132 milliseconds.
Correct.
Oh, okay.
So right now the reasonable field resolution is around 10 nanotesla. That's the best we can get.
For a 1 second resolution, for a 1 second sample. Yep.
But if you sampled, well, how many samples is 132 out of 400? I'm going to have to do the math here.
Well, the way it works for the cycle count, for the cycle count of 400, you're taking 1 sample in 15 milliseconds.
So that's 132 milliseconds is 53 samples at 400 hertz.
No, it's not the way it works.
Well, I understand you got the rolling average, but it's a total of samples that are averaged.
Well, the way it works is that if you set a cycle count, let's say of 400, and you measure the time it takes to complete that 1 sample, that's considered a single sample.
So 400.
That is 50. That is actually it's a little under 15 milliseconds. So there's some overhead, which if you multiply that by 10 when you're taking 10 averages, comes out to 132 milliseconds. So it's approximately 13 and a half milliseconds to do 1 sample with a cycle count of 400.
That would be a delay, not a sample rate.
Yeah, that's
well, the sample rate
is how fast the data is coming back from back-to-back samples.
Well, the way this thing samples, it counts up and counts down.
Yeah, you need to distinguish between the sampling of the ASIC, the number of times the individual coils on the sensor are sampled by the ASIC, which and the actual observations that get reported out. we're taking, it's using 400 measurements of the field coils, but it's using 10. It's using a moving average of 10 to report out a single observation that's reported every second. Is that correct?
Every second or 132 milliseconds. That's where I'm
Well, I
confused.
don't know where that 132
Well, okay,
milliseconds.
if you do a single, if you set the average to 1 or 0, okay,
Right.
set that register to 1 or 0, and you set the cycle count to 400, okay?
Mhm.
To take a single measurement, the magnetometer actually counts up to 400 or counts up and then counts back down again with a reverse polarity of the looking for reverse polarity of the induced field change in the inductance of the coil. That gives you your final answer, but that's a single measurement. It's not multiple samples. It's a single measurement. Now, what we're talking about is taking 10 of those single measurements and averaging them. And that's what takes 132 millisecond at a cycle count of 400. If you drop to a lower cycle count, you get also at a cycle count of 400, you get a higher resolution than, let's say, a cycle count of 200.
I know what's confusing. It's not 400 cycles per second.
Correct.
It's just an arbitrary 400 cycles of whatever your oscillation rate is in the coil.
Correct.
It's 400 hertz of oscillation in the coils that you're setting it to.
No, that's not hertz.
Nope.
Not hertz.
He hasn't specified the actual cycle time.
Yeah,
So-
cycle times and it's not related to seconds. It's whatever the ASIC is.
The only thing that is 1 second is what the code, how often the code reads the result register. And so that's an observation, I think you might call it, that by the device that we're reporting out. It's not anything physical about the system.
So does it count 400 up and then 400 down, you said?
It's basically doing that, taking a time difference because the field, the Earth's or whatever local field is around, essentially affects the inductance
The zero
of the
crossing.
Right.
Yeah, I
and
understand.
so right, and so but also
So
by
a cycle
reversing-
itself, if it's 132 milliseconds to do the whole thing, then one cycle time is it's about
13
165
milliseconds.
microseconds.
Well, no, actually, again, we're talking about 10 averages. That 132 milliseconds comes in 10 averages. Each reading of a 400 cycle resolution, and that's a resolution, is 13 and a half milliseconds.
Yeah, okay.
Okay. So you take 10 of those and average them. That's supposedly, if it's a random noise, then supposedly you get a factor of square root of 10 as an improvement, but you don't quite get that. And also, if you increase if you increase the count rate past 400, according to PNI, you then get into an area where you're probably not seeing any improvement in noise, and it may flatten out. So 400 is about the highest they recommend for the cycle count.
Yeah.
So if we run it at 400 sample count rate and then have the thing average for 1 second, that will give us a better number than if we were doing it every 10 for 132 milliseconds.
Yeah, you could do that. You could do that and increase the average to, let's see, I think I computed an average.
7 better.
I think I computed an average of 40, and to do an average of 40, it takes approximately 400 milliseconds.
But if we ran it for as long as we could for a second to maximize the minimization of the noise floor, I mean, that's ideally that's what we're after, right? Because we only need a 1 sample per second report.
Right. You'd have to do some experimentation on that because it may not be. There may be some trade-offs. It may not necessarily follow the square root of number of averages in terms of reduction of noise floor.
You also may get some noise from the transmission of the data. So
Well, there's that too, of course.
As a side issue, I've been reading, I don't know if it's true or not. I'm not saying it is, but I'm reading that the Raspberry Pi 4's Ethernet hardware is quote unquote noisy in terms of creating electrical noise for other devices, not the network itself.
Yeah, that's true. That's true, Dave. I've run into that with some audio recording stuff, and there's a for the specifically for the wireless thing on the Raspberry Pi. During the wireless beacon, the extra load on the power bus introduces a slight glitch, which does couple through to other devices, and I've experienced that with some audio stuff. However, I have not seen that in the magnetometer, where the magnetometer is located remotely.
Good to know. Something to keep in mind, though.
So 10 nanotesla resolution seems to be okay, but I mean, assuming that we don't have to worry about any other technical issues, how better can you go
that,
in terms of resolution?
I sense a 1 nanotesla resolution desire there.
Oh, I think that's one of the differences. It's going to be really big. It's going to be a completely different story right now.
The scientists always want more.
Of
They
course.
always want,
You would be a
better
scientist.
on your resolution.
So you're going to have your a field out back, and you're going to have to put a mesh array of these up to phase them so that you can.
Yeah.
No, never mind.
Well, get more installed and do some experiments. Then you'll find out.
Yeah.
Yeah, I wonder if I can ask a question. At the beginning, there was a discussion about a Pi UPS. Can someone give me a link or the name of that device so I could put it in the notes?
I suspect.
Yes, it's the I've got one here in front of me. It's called the Pi Uptime UPS 2.0. If you just do a search for that, you'll find the source for it rather quickly. It's carried by, actually, there was one on Amazon. There was one on, let's say, Tindy. But at any rate, the source you want, the site you want rather, is Pi-Uptime UPS 2.0. And just do a search on that and you'll find it.
All right, thank you very much.
And I have one right here in my hand for should anyone be interested.
There's a link in the chat room if you'd like.
The nice thing about the thing that Dave is holding, it'll take two 1860 anyway, two lithium poly cells, 3-volt cells, or that unit will also take an external lithium poly or nickel, lithium iron phosphate battery for as long as an hold up time as you want.
There's a picture of it if everybody can see that.
Yeah, that's the one.
And you can buy on eBay, Amazon, or Tindy. There you go.
Yeah. So what kind of uptime roughly does it provide? Any rough estimates?
Well, it depends upon the load you're running. The basic, those two cells, those two 3.7 volt cells will give you up to 3,400 milliampere hours.
Okay.
And of course, if there's obviously a voltage converter to give the 5 volts into the Pi, so you can look at that total ampere hour that's available. But if you use an external battery, you could put easily a 10 ampere hour lithium iron phosphate battery on there and get as much uptime as you want.
Okay.
And with a solar panel to recharge.
And it'll do 2.5 amps of power in the converters. So plenty to run the Pi 4 and the magnetometer. John might run the grape station too. John, you're muted.
Talking to myself again.
Oh.
And I keep answering myself too. The lithium ion batteries cannot be used outside because you can't charge them below 32 degrees F, they explode.
Right. However, you can use the lithium iron phosphate batteries down to low temperatures.
Right.
And that's what I've got here. That's what I'm actually using, external batteries.
that's what I was talking to Scotty with last week. We brought in that diode board for the plus 12. You could use one of those 7.2 ampere hour gel cells and have it, it'll run the thing at 12 volts for 70 or 80 hours, which will get you through a power fail very nicely.
Right. And of course, if you have a station UPS and you really don't need this, this is
Right.
kind of for standalone pies, which is the situation I'm in here, right?
Yeah, I've actually got a gel cell on mine to get it through the hiccups.
You don't have power outages of 8 or 10 hours, do you?
We just had one that was 11 hours, which is the longest one I've been here since 1984. That windstorm that came through 2 weeks ago took out so many substations around here. The power was out for some people, it was 5 days. It was horrendous.
Oh.
Yeah, well, in New England, we can have very extended power outages.
We
5
have them here
days,
too, except they're
weeks.
usually due to tornadoes.
Yeah, ice storms are the big ones here.
Yeah, there's all kinds of
We'll get
nasty.
those too.
You put it as underground, so it never happens.
Well, actually, our power is underground, but it's fed at the end of the street by above ground, so it's and the substation's above ground as well. So unless you get everything underground, it doesn't work.
And also, tornadoes will take out the big main feeder lines coming from Alabama Power or TVA. You know, the ones that are 100 feet tall.
Yeah.
Knocked down. The last tornado came through. It knocked them down on both sides of town, and so knocked up primary and the back out.
Yeah.
Well, of course, we had a big ice storm in '98, and local towns were down for 2 weeks. Up in Canada, it brought down the big transmission lines. They were down for several months.
That's nasty.
So get a generator.
While we're taking a break, can I ask my question about GNU radio?
Yes.
All right, let me share my screen here. Let's see. Okay, I think this is the one I want to share here. All right, you see that what you're looking at there is about something like 12 hertz bandwidth. Can everybody see that?
Yes.
And the FFT on the top is I think it's a 4096 bin FFT, and that's how much data it is output. I started at 3 o'clock this afternoon. That's how slow it is. And in the middle, you can see a little squiggle there. I believe that's sunset. And where the color changes, I believe that's sundown. But you see how slow that is. Now, let me just stop this and show you I want to have some I'd like to get some advice on how to set this up. I talked with Nathaniel about it this afternoon, and he said I needed some decimation because, like, for example, I've got the decimation set up to 4,000, and in order to get the bandwidth small enough, let me show you what it looks like if you just use 1 and 1 here. Okay, so there you see it running just directly as it comes out of the machine. Of course, these scales are not correct now. I didn't change that. You'd need to show what the bandwidth really is. It's the sample rate, because bandwidth here. All right, so that should be, yes. So now you got a 48 kilohertz bandwidth because I'm using the 48,000 samples per second and coming off of the flex radio. IO samples, which go into the UDP input on GNU Radio. So if I wanted to do something comparable with what Steve Serwin has been doing using Spectrum Analyzer, where you get, I don't know, an inch or two of display per hour. I think that's what his data looks like. How do I set up GNU Radio? Because see, you can't see a fraction of a hertz deviation at this speed. But when I set it with the decimation high enough so that you can see the sub hertz resolution, then it runs so slow that so if I put this back up to 4,000, we'll change this so that the scale displays correctly. So my question is this what I'm supposed to be doing here? Using a decimating FIR filter? Is this the right way to do this?
Yeah, so what that filter does is it's a low pass filter. And so it will, I don't know where you set the parameters on it, but if you have a 48, if you're decimating by 4,000, then the output sample rate will be what, 48,000 over 4,000, right? So 48K divided by 4,000 is 12 hertz. So it's got a 6 hertz low pass filter. So it's filtering from minus 6 hertz to plus 6 hertz. And so when you then run a 12 sample per second sequence into an FFT of size 4096, then it's going to output one FFT buffer every it's going to output 0.003 buffers per second. And so if we invert that, so 1 over 0.003
300 seconds, 300 seconds or something.
Yeah,
341 seconds.
Yeah, that's about right. But
yeah, so
and,
right.
But it seems that this is necessary.
It's about like you'd expect.
Get something about every 5.75 seconds. Or minutes, I'm sorry.
And what is this giving me as far as resolution in hertz?
Okay, well it'll be 12 divided by 4096.
Okay, so that's actually more resolution than I need.
That's 3 millihertz.
Yeah, it's giving you 3 millihertz resolution, roughly.
Yeah, so I think, Nathaniel, what have we been talking about that we need as far as resolution to see the excursions that we want to see? It was something like we've been shooting for 10 millihertz, right?
Yeah, that seems about right. 0.1, or is it 0.01 hertz?
This is on what frequency?
10 megahertz.
10 megahertz? Well, I'll just say for our AM Doppler experiments, we're getting measurements at about the 10 to the minus 7th level. And that would scale with frequency. So 10 to the minus 7th from 10 megahertz
would be 1 hertz.
It's about a hertz, right? So you'd want it to be probably at least 10 times better than that, but then
yeah, I would think if you could get at least 0.1 hertz, that's good.
Well,
0.01 is better, but at least getting 0.1 hertz.
But isn't that going to be your span across the entire display? So I mean, you really don't need that kind of resolution. You need something you can see, but not like 0.1 hertz across the whole
Oh, right, not across the whole display. You want to be able to see about probably up to 5 hertz on either side. So probably a total of a 10 hertz bandwidth.
That's this. What I've got here is 12 hertz bandwidth.
Yeah, that should be fine.
Yep.
And that is, the problem is when I do that, the rate is so small, the rate is so slow that it's hard to, I'm just not finding the right combination of
And what's
Yeah.
So you're playing 4096?
He should be getting a new FFT bin fill every almost 6 minutes. It's 340 seconds.
See, because when we were doing this with Spectrum Analyzer, I think we had an FFT of 216,000 or something, and we were getting a new one every, I don't know, 40, 50 seconds or so.
Mm-hmm.
So were you pipelining them, or how were you getting them that fast?
I don't know. I don't know how Spectrum Analyzer works internally.
Yeah, so an FFT, right, is very straightforward. The resolution of the FFT is the input bandwidth divided by the number of samples in the FFT, and the time it takes is the input sample rate times the number of samples. So if you're going to resolve 0.01 hertz, it's going to take about 100 seconds to do it.
Mm-hmm.
Yep. Then also, if you're 12 hertz and you do, say, a 1024 FFT, it's going to be 12 millihertz resolution.
Say that again.
If you have a bandwidth of 12 hertz, that it's going to be 12 hertz wide, and you do a 1024 FFT,
okay,
your raw resolution is going to be 1,000th of that, so about 12 millihertz.
Yeah,
so it might be 10 times more than you need. I don't know.
Bill, that bandwidth label there doesn't change the computation. All that does is scale the display axis.
I know.
Okay.
I'm just trying to. I just wanted to show up correctly so that, say, we'll try that on the.
Bill, I mean, if you're doing 12 hertz of bandwidth and you do 512 samples, 512 divided by 512 is 0.023. That gives you 0.02, 200ths of a hertz. That might be good enough for this display.
Yeah, Bill, one thing you may find convenient is to declare a variable called decimation, and then you can put that into all of your different parameter fields. And when you change the variable value, then everything everywhere will adapt to the correct numerical range.
Now I did see that, Tom. However, it didn't update. I had to stop and start the run in order for it to take.
Yeah. Yes. It's it's done. It's loaded initially when you start.
Yeah. Okay.
But you could put a slider in, can't you?
Yes. Although I don't know that you can do that with decimation, because you would have to recompute all the filter coefficients in the decimator every time you adjusted the slider. And I think what it does on start is it looks at the decimation value, and then it goes off and computes all the filter taps, loads the decimator, and then starts. So I don't think you can adjust the decimation ratio in real time.
Okay.
All right.
By the way, just an aside, I'm hearing the Brazilian time signal station right now on 10 megahertz. Not WWV. This is in New Hampshire.
Wow.
Well, that suggests that the plan to observe the eclipse might be very successful. The clip's going through South America later this week or
Right.
whenever it is. All right, so recommend me a good set of parameters here. If I'm getting my data at 48,000 samples per second.
Yeah, so a recommendation is you probably want to decimate it. I think 10 or 12 hertz is a good number, so decimate it by 4,000 or 4096, whatever 4,000 is probably plenty good. So decimate it at 4,000. That gives you now a 12 hertz sample rate.
You need
So
more taps than one.
How many taps do you need?
Normally, if you leave taps blank, I think it auto computes the filter for you. I'm not sure. You can try that and see if you get an error. But normally, there's a value that you set the taps that it's smart enough to know how to compute the taps for you.
But
Now set the FFT size to something like Nathaniel said, 512.
But Tom,
No, it does require you to input the number of taps because it didn't.
Okay, I'd have to look at the manual. There's a magic number I think you can put in taps that will cause it to pick a good set of taps.
If you click on the documentation tab, does it tell you?
Maybe.
No.
It gives
Okay.
it sends you to
anyway,
Wikipedia.
I'd pick something like 128 or some nice power of 2, or something even smaller, 64 maybe, just to try it. If you got to put something in, it determines the transition zone, right? The number of taps.
Right.
Yeah. And if you pick something like, it may be 0 is the magic value. I think there's a magic value on taps, and it will
Actually,
figure it out for you, but start with 64.
If you pick 63, pick an odd number, because then it can make it a symmetrical filter. If it's smart enough to do that.
And then set your FFT size to maybe 512. And then set your bandwidth to sample rate over whatever you decimated. And yeah, make that FFT. You have to make them the same. There's certain rules that you have to meet. Otherwise, you get 2 different ports trying to run at different sample rates, and GNU Radio doesn't like that.
Speaks a different language.
Yeah.
I think that's where the setting the variables would come in really handy.
Yep. Yeah.
Well, yeah, I mean, I had a variable in there for a while, and then when I realized you had to start and stop it anyway, I took it back out as an unnecessary complication, but it's trivial to put back in.
Yeah,
All right,
I think it's
I'll run
less
this.
for turning it off and turning on, and more where you have to reuse
Yeah.
the
Yeah, I know what you mean. Yeah.
Yeah.
Yeah, so it's going to take a while, but what you get, I think you should get a measurement out, every 2 minutes or so? Well, of course, we're using the 512.
The 512.
That should run a little faster.
There you
Okay,
go.
there it is. There's your first reading. So anyway, I will do some monitoring on this and see what it looks like overnight a few times. Then we can discuss it further. But how important is this? I don't know. But the main thing on this is that when we get the local host cranked up with the data engine, you got to be able to look at something to make sure you've got it set on a usable frequency and that you're actually getting a signal all the way from the antenna out to your analytical point. So that's why I thought it would be very important to have at least some kind of a graphical output.
Mm-hmm.
And I'm not up for trying to write all the QT stuff to make it happen on the Pi. It's theoretically possible, but a lot more work than is necessary since we have GNU Radio. So anyway, thanks for the input on this. I'll keep you informed on what I learn on it. Back to Net.
So since Dave's not here, we'll mention that we are about 20 minutes over. Unless anyone has anything else, I got a little clip to show people if they're interested.
Let me stop sharing here.
Unless
Okay.
it's something else.
Take it away, Scotty.
Okay, I don't know how many.
Yep, Scotty.
I don't know how many people have seen this, but it's fascinating.
Oh, cool. I've not seen this.
It's about 2 minutes.
Scott Manley also had the one taken by the drone.
It's on here next.
Oh, that hurts to watch.
Now watch the tower in the background.
If you listen to the original recording with good headphones, you can hear this otherworldly thump when all that equipment hits the ground. It's scary.
Yeah. Next up, they have the drone inspecting the head there when it collapses.
So what is it, a cable failure or is it something?
Yes.
It's a cable failure is what it
Yeah, in
looks
fact,
like.
Angel was saying they could hear the strands
Look at the
snapping all
middle,
weekend.
the middle cable there.
Oh.
You can see it just come apart. And then bang, 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 all of them go at once.
Yeah.
But watch the remote tower when the drone backs up. One of the three tower, that tower there. I think that's the one. The cable cuts it off and it collapses. The top piece collapses.
I think all three towers lost their tops.
Yeah.
There was a link that Nathaniel sent, I think, that Tim Duffy interviewed Angel on the DX Engineering YouTube channel. And you can go and take a look at that. So he talks you through this.
Anyway, thought everybody would be interested in that because if you haven't seen it. Anyway.
Thank you for sharing it, Scotty. That was good. I've never seen that before.
And if you just go on YouTube and search for Arecibo, there's a whole bunch of news stories and this clip in lots of places.
Yeah, I'd read one analysis of that. The top of those towers were actually pulled down by the backstays. They lost the counterbalancing force on the hanging instrument, and they just ripped the tower back the other way.
Pulled them all off. Oh.
Yeah.
But the whole head weighed 450 tons.
900 tons.
900 tons.
900 tons.
2 million pounds.
What kind of tension in those cables?
Whew. Tremendous. Each one, let's see.
Like they were
Angel said something about each cable was 20,000 pounds. And their best winch was 10,000 pounds. That's why they were not able to bring the structure down before the cable snapped.
Yeah, the cables must have fatigued over the years, and they had a couple of earthquakes and 3 hurricanes in the past year. So
right. Well, those were original cables from 1963. They had added auxiliary cables, which one of those was the original one that popped when they added to the structure, added that big dome and the Gregorian reflector. And yeah, there was a lot of force on those cables.
So
those were bridge
cable
cables. They're the same sort of thing you use on suspension bridges, but I suspect that the earthquakes fatigued them pretty severely.
But did they know they were going to have problems before they knew there was a problem before it collapsed?
No.
They didn't.
Well,
I mean, they had evacuated it.
Well, yeah, no, the first they had one of the auxiliary cables popped an attachment. And then from the increased strain, one of the main cables broke in November. The original failure was in August.
Ooh.
Then they had a main cable snap in November, and that pretty much sealed its fate. Because then the remaining cables had to take all the weight, and they just weren't up to it.
Being 60 years old doesn't surprise me. Just corrosion alone would scare you.
Yeah.
Are you coming up on 60, John? Is that what you're thinking about?
I'm
is that the
61, so I'm already ready to snap.
I got more than that.
Scary
I
thing
snapped
is,
years ago.
we got a bridge here that's over 100 years old with those cables on it. Makes you kind of think.
Yeah.
Yeah, it does.
we had a bridge going over the lake that was actually built before the Civil War.
Ooh.
And it was a single lane one, but people still drove over it. And I was just wondering, how long is it going to be before that collapses? Well, fortunately, somebody helped us out on that, because somebody tried to drive a truck pulling a pretty large backhoe or track hoe or something that was up high enough it didn't fit under the bridge. So as he drove through it, it ripped out the top of the bridge, and the bridge kind of collapsed behind him. So he was like that guy, the luckiest guy in Iraq, where the bridge blows up right behind him. So that bridge was, it took him about 1.5 years to get it replaced. They put in a modern concrete one. The problem was that the people who lived on the other side of that bridge had to drive on a dirt road through 5 miles of mud to get to the main road, because the lake was in the way.
Oh, geez.
For that 1.5 years. Oh, there you go. Tacoma Narrows.
This bridge here was designed by a graduate of the college I went to. So, needless to say, there was plenty of this film shown during physics classes and mechanics classes and things like that, because apparently the guy didn't properly account for the resonances.
Yep, one word, resonance.
And they have a picture. I don't see if they show it on this film, but they have a picture of a guy running toward the camera on the bridgeway. Some crazy guy who was out trying to measure stuff when the bridge started doing this kind of thing.
Oh, jeez.
And I guess he got off the bridge okay, but some people don't have much sense.
My Dartmouth advisor did a physics text that he included this video, and he showed it 2 different ways. One in the Earth reference frame, and then the other in the bridge reference frame.
Okay.
So you're seeing the bridge rotate around the camera.
Oh my God. This is a bridge cable support, right? That we're seeing here?
Yeah. Wow.
By the way,
I thought the guy that was on the bridge was trying to rescue a dog or something.
Yes.
Oh, maybe so, yeah.
He was.
Yes, a couple of years ago,
Here we go.
I saw an article about how this bridge was collapsed. Like, it's kind of like a professional paper, and the paper claims that the reason why the bridge was collapsed is not because of the resonant frequency of the structure, but because of turbulence that is caused by this resonance around it. So that was a different point of view of analyzing how the bridge was collapsed. Kind of interesting.
By the way, I just put into the chat a link to the interview with Angel WP3R. He's the director of telescope operations at Arecibo.
Where's the dog?
Doing something very unnice in the car.
I think I'd do something unnice if I was trapped in a car. That was
man. It's actually a suspension test for the car.
Yeah. I don't think the car survived.
I don't think so either. Wow. There we go.
Interesting, though, it wasn't a cable failure.
It was a surface failure, right, of the roadway?
Yeah, it was the roadbed. Cables are still there.
Anyway, our university caught a ration for all this, for one of our graduates designing this bridge, the Verrazano or Tacoma Narrows Bridge. So it was a staple of all the classes. Anyway, enough of that. Just how do I stop this here? Okay. So the featured short.
Are we done for the night?
I think. Anyone else have anything else?
I don't
I
think
think
so.
that's it for me.
All right, thanks, gentlemen. 73. We'll
Okay.
catch
73,
you
Bill.
all again soon.
Hey, Scotty,
We're on. Yeah, just say we're on for Thursday, right, Nathaniel? This week?
No, we're
No.
this is not not this week.
Okay, got it.
you can get this to reach.
73. See you next week.
All right, 73.
73.
All right, we'll see you.
73, everybody.
73.
So, John, you looks like you have an earthquake there. Oh,
That's the clock I was talking about.
clock board, yeah. The one you sent me the